Hi folks, we're back to talk a little bit about the ultimate product that many geologists work on, and that is geologic maps. And if you have seen already, I have put in this segment some different problems for you to look at. And so one of them looks a little bit like this. So this is on the geologic structures sort of diagrams that I have in here, and I show this sort of structure like this. And what I've done, what you're looking at here is a map where a geologist has gone out and has said, here's a formation that crops out here, here's another formation that crops out here, and so forth. This is not topography, and it's not contours even for that matter. These are what we call contacts. And so a contact is where two formations come together. So contacts are these sorts of features. And they help us, well, here, a formation is the fundamental unit of geology, pretty much. It's a mappable rock unit is what we call it, a mappable rock unit. And so formations can have contacts on them like this. In this case, in the first example here, I actually put on some strike and dip symbols on here as well. And remember, in a strike and dip, this is the strike direction, that's the dip direction this way. And so this indicates that those beds are dipping away from this structure right here, whatever that structure is. Well, you can kind of see that there's a symmetry to it, so we could draw a line through the symmetry. So this half looks like that half, essentially, right? And so, in fact, if the beds are dipping away like that, this is, as it turns out, an anticline. So that's the symbol we use for anticline right here. Now you know the strike and dip symbol. Here's the plunge direction is off in that direction then. And so this is rocks that have been folded. Let me show you an example. I know that's Walden. It's a little bit thick for a book. Here, let's get one of these. You folded it like that, like an anticline, and then you're plunging it, and notice how the beds plunge in the direction that the anticline, the beds seem to close here. So it's plunging in that closing direction. So that's what you're really looking at here, something that's been folded like that. And so this is a plunging anticline. That's the first example that you have here. Let's go on to some of the other examples that you see as well. So formation is defined as a mappable rock unit. Let's see if I can't get a little bit better marker here. The second one just shows some dipping straight, it looks like. Here's another map surface. Yeah, this is a much better marker. Map surface looks like this. There's a shale up in the corner. The symbol for shale is this sort of dashed sort of lines like this. Here's a sandstone. International symbol we use for that has dots all over it like so. And then there's another sandstone over here. Dot, 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 dot. And, okay, so what I do in this diagram is I tell you that that is unit D right here. This is unit C. And that's the same unit C that's over here. And this is unit A, or excuse me. Yeah, this is, yeah, I'm missing one of my units in here. Okay, so let me take that out. That's C. And this is actually B in here. And here's B over here. C's over here. So there's B again, and here's A. Now, I ask you, what kind of structure is that? And you don't know. There's one of two bits of information that you need to know, right, when it comes to structures like this. You already know that old beds dip towards young beds. But you don't know what ages these are, right? So if A happens to be the oldest, that means that this must be an anticline because the beds then would be dipping that direction, right? So they'd be dipping away in that sense, like this. So if A is the oldest, and so there are two bits of information we have to know. So for instance, if you saw this sort of diagram with just a bullseye on it like this, and I asked you to interpret that, there's no way you could tell me what that was unless you either have the age or the attitude. So in this sense, I say, well, what if it's the oldest? If A is the oldest, then the beds dip away from it, right? So that would be an anticline. Here's the axis of it right here, symbol for an anticline like this. Now, no plunge direction you see on this one. It's just a simple anticline. So in other words, what you're looking at is this type of surface, right? I'm going to bend it a little bit so I can do that. That's an anticline right here. So if you cut the top off of that thing, chop that off, you're going to have the beds dipping away. The two limbs of that anticline would then be dipping away from the axis, and so the axis runs right through here. And so the symbol that we put on that axis is like that, and that means anticline. Just so that you know, here's the symbol then for a syncline, where the beds dip towards the syncline. Those are really two arrows that come together right there. So two arrows coming together, that's a syncline. Two arrows pointing away, that indicates that the limbs are dipping away. And so that's the symbol for an anticline. And if it turned out that there was a plunge on any of these sort of structures, you'd put an arrow at the end towards the plunge direction. And so that's some of the more symbols that we use in geology. I discussed the attitude symbol much earlier in here and how it is represented on geologic maps. So, okay, now what if A was the youngest? And then if A was the youngest, this would have to be a syncline then. So you have to know one of those two things. What's the age or what's the attitude? So here we are. That's the second one. For the third one, here's our square here. Bullseye, right? There's a bullseye. And I tell you that that is the oldest right there. So if that's the oldest, these beds must be dipping away. It's just one of the rules we have, right? So we talk about superposition, right? So the oldest beds are going to be at the bottom and the youngest at the top. And if we turn it, we push up from underneath, the oldest beds, if you were to rotate it, are going to be cropping out in the middle here. So that, in fact, is a dome. That's the type of structure that you have here. And you can have the strike and dip symbols. If it helps you, old beds dip towards young beds. So if I say oldest, make sure you put the dip symbols away from it like this, and you can interpret that sort of structure then. That's a dome. That's number 3. Number 4 on the structures. I show it like this. Fold like this. It's folded because of the pattern that it makes, right? It's closing in one of those directions, so it has to be folded, right? Otherwise, it'd be just one single unit across there, right? If it was not folded at all. In this case, I'm showing you strike and dip symbols. The attitudes are going like this, and that, and like that, and like that. My dip is heading off in that direction, so strike this way. So this one's dipping to the west, that's dipping to the west, that's dipping to the east, that's dipping to the east. And so therefore this has to be, and here's the symmetry, right? There's the line of symmetry runs through there. If the beds dip towards the axis of a fold like this, in this case, we're looking at a syncline. So here's my double arrows pointing inwards right here. What direction is it plunging? And now remember, we always have north towards the top like this. So in fact, this one's actually plunging to the south down here. So you'd actually put on the plunge arrow like that. And that's how we'd interpret that sort of structure as well. All of this sort of information like this has to be gathered by geologists that go out into the field and map these sort of structures like this. They try to walk out the contacts if they're in a place where they can actually do that, like the American West, where it's very desert sort of conditions out there. It's easier to walk around, and you can actually map and take elevations, GPS points, and so forth. And so you can have control points all over this map. in order to define that structure. So there is number 3, or number 4, that is, actually, number 5, I got it off over here to the side. Here's my symbol, like this, and I put a 45 next to it like this. What is the dip direction? The dip direction is to the northeast. What's the dip? That's 45 degrees. That's the deviation from horizontal, right? And so that whole, this whole thing is dipping like that, right? So if you were to see it on the edge, it would look like that, right? But those beds would be going into the rock like that, into the surface. And so what's the strike on it then? Well, this is where we use that right hand rule, right? So the strike is off towards my thumb direction out here. And make sure I'm using the right one, because there's a different British and a different American right hand rule. Yeah, this is what we use for strike out here. In Britain, it's more like that, right? And so in this case, if you're in Britain, it would be the strike direction would be reported down this way. And I try to draw this at a 45-degree angle, not to confuse you, but to go, okay, well, here's our 0 up here, right? And so you go around, here's 90 degrees here, keep going, 180, 225 over here, and then another 45 on top of that. It's about 270. Oops, oh no, that's not 225 there, that's 270 right here, plus another 45, so that's about 315 then. So that's the strike direction right here. And geologists would report this as 315 degrees, 45 degrees to the east. It's why east, because it's more to the east on that side. If it were over plunging like, if it were dipping like that, if it were dipping like that in 45 degrees, let's say, first of all, the strike would be down here. 180 plus 45, so it'd be 225 then, and then 45 degrees, but then it'd be to the west. Okay, so it's farther to the west over here where its dip direction is. So 315, 45 degrees is that symbol right there. Okay, so the symbol that's next on here shows you another fold, and it's this symbol right here. Here's my plunge direction. You already know that, right? Here's this symbol right here, 2 arrows away like that. Well, this has to be a plunging anticline then, right? So what's the plunge direction? Off to the northeast, right? Can anticlines and folds actually have bends in them like that? Yes, they can. And the reason they can have that sort of a bend in there is because they have been refolded. Okay, you fold it once, and then you fold it again from slightly different direction, and all of a sudden you have a refolded fold. And so that's a plunging anticline right there. That's the end of page 1 on here. That's the 1 through 6. Number 7 shows a block diagram. So block diagrams, as you recall, have a top surface which indicates the map area. And then they have 2 cross sections on here. And so I'm showing something like this. That comes up like this and then down like this. And so essentially what you're looking at is some sort of fold that looks like that. It's a pair of folds, in fact. So here's my anticline right here. Here's my syncline right there. And the beds seem to be dipping. Well, here's a, see, B, this, the axis of this thing runs that way. The axis of that one runs that way. And they're closing in that direction, right? So that's the plunge direction right there for both of them, as it turns out. This is my syncline on that side, my anticline on this side. So, sorry, made a little bit of a mess out of that, but that is the block diagram. And so I've left off some of the beds, obviously, on there, but that's the type of structure that is, and that's at the top of page number 2. All right, we're in the middle, and I guess it's number 10 now. What type of fault is this? And so I show you a cross section here. Now remember, just to orient you, a cross section would be like the front of a block diagram. If you could actually go in and plunge in and take a block out and you look at one face of that block, that's what you're seeing here. Here's my fault plane that runs through here. I show a coal bed right here and a coal bed right here. First of all, the first thing you have to ask yourself, which side's the hanging wall? Well, hanging wall is this side, right? Because that's not the side you could walk up if you're going like that, right? This is the side you would be able to walk up by going like that, right? So foot wall on this side, hanging wall on that side, and because the coal bed is now higher stratigraphically on that surface, it means it's going like in that direction, like that, and like that. And so the hanging wall has moved up. And so first of all, you would have to say it's a reverse fault. And the next question you have to ask yourself, what is the angle on that? So it's roughly 30 degrees or so. So therefore, it is a subset of reverse faults known as a thrust fault. So that's a thrust fault right there. And that's the sort of thing you get in the Appalachians, right? Usually facing the other direction, however. So that is a thrust fault. That's number 9. What type of fault? Well, that's number 10. Number 11, mark the foot wall and the hanging wall. We just did that. Here's some more. So here's another cross section, and another cross section, and another cross section right here. I show one like that, and one like that. Which side's the foot wall? Which side's the hanging wall? This is going to be the foot wall, right? So you could put steps on it like that if you wanted to. And you can imagine walking up that surface. That's the foot wall. The hanging wall is over here. The hanging wall's on this side over here. It doesn't matter, you know, it's not like it's always on the right or it's always on the left or anything like that, right? You know, and down here, the foot wall is always going to be on the bottom, I can tell you that, and the hanging wall over here. So those are the hanging walls and foot walls in each one of these types of faults like this. So can you tell what type of fault that they are from the available information? No, you cannot. And the reason for that is we don't have a key marker bed on any of these, right? So there's no way to know. Well, if this one happened to have a bed there that was the same bed as there, here, let me draw it up a little bit higher. Let's say that bed's the same as this bed. That means that the hanging wall has moved down, and that would be a normal fault. So you have to have that key marker bed in order to figure that out, though. Because otherwise, if we had a bed here that's the same as this bed down here, that means it went this way. I made a mistake. I think it was like on the very last diagram when I was talking about rift zones, right? And so we talked about a rift zone being something like this, and I put my arrow the wrong direction. It should be like this. Okay, so it's going down in the middle in a rift zone like this. 2 normal faults, essentially bounding a rift zone. But anyway, in this case, you don't have enough information unless I actually put on there a key marker bed. Okay, let's take those off. We're now on page number 12. How old is the Earth? 4.56 billion years. How do we know that? We know that from absolute age dating of zircons in granites. The oldest rock that we know of is actually 4.28, I think, is the oldest rock. 4.4 is the oldest zircon that we know of, and we know that many of the moon rocks, in fact, are roughly around 4 billion years as well, a little bit older than 4 billion years. And then some of the asteroids that we've been able to do age dating on, they all hit around 4.55, 4.54. Sometimes 4.56. Okay, number 13, what's the age of the oldest rocks in Missouri? You got this from the presentation. They're Precambrian in age. And now Precambrian is a funny term. All it means is it was before the Cambrian. But Cambrian is a very special unit, a rock time period, if you will. If you take the geologic course, it's called historical geology. We talk about time in consideration. Now, that's not the part of this class that we spend a lot of time on, however, but Cambrian are the first complex metazoan fossils that we find in the rock record. As it turns out, 90% of geologic time is in the Precambrian, but those rocks are not very commonly exposed, but they are exposed in eastern Missouri, southeastern Missouri, in the St. Francis Mountains around Ironton and Farmington. Okay, so that is number 13. Number 14, what layer comprises the largest volume of Earth? That's the mantle. 75% roughly is mantle. Okay, this is one we haven't encountered before. I'll show you a cross section here. And this is actually much like the rocks in Nevada and Utah. And I show you this sort of diagram like this. And these are fault planes right here. And this is not a term that we've actually approached yet, actually. I had hoped that we would do this previously. I wish we'd had more time in the class. This should have been in with the faults a little bit. But what I'm trying to indicate here is this area is going up like that, and like that, and like that. And in the Great Basin of western Nevada and western Utah, eastern Nevada, faults like this very commonly occur. And what happens is they have this sort of tendency, and immediately you're going to say, I recognize what type of fault that is, I hope, like that. And if that goes, it's going up that way, right, and down this way, and down on this side, up on that side. This would be the footwall. That's a hanging wall. That's a footwall. That's a hanging wall. That's a footwall. That's a hanging wall. This is a hanging wall. That's a footwall. Footwall, hanging wall. I hope you get this right. So here is the hanging wall. Here's the footwall on this side over here. This is going to be the footwall over here, and put the hanging wall over here. Hanging wall, footwall, footwall, hanging wall, and then again, hanging wall and footwall there. And if we keep going over here, this is going to be, of course, the hanging wall over here, and this is the footwall on that side. So anytime you get a fault like this and you're showing motion on it like that, you know what kind of fault it is. If that's the hanging wall and it's moved up relative to the footwall, it's a reverse fault. Easy enough, right? But that's not what's going on in any of these, right? So there's our footwall right here. What we're looking at instead here is this side going up and that side going down. That's the hanging wall, that's the footwall right there. And so if the hanging wall moves down relative to the footwall, it's a normal fault right there. That's a normal fault. 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 And if I had the arrows on it here, you'd see that this side has gone down relative to this side because these blocks are going up, right? Each one of those 3 blocks. They have a special name for the 2 blocks, the 2 parts of these things. When a block goes up like this and it's kind of bounded on both sides by a normal fault, here's another block that's gone up, bounded on both sides by a normal fault. And again, the same story. Normal fault, block is going up this way. This is referred to as a Horst. It's a German term. Something like a gravestone, I think, is what the interpretation is. So it's, if that's the grave, that's the grave marker, these things in between are known as grabens. And so this sort of structure like this is a graben right here, this is a graben here and here, and over here, that's half of one. So Horst and graben are defined. That type of topography like this is defined by the normal faults that break that landscape to pieces, right? And so what happens when you do that? Well, if you think about normal faults being associated with tensional forces, that means that this block and that side over here and the whole terrain has been pulled apart essentially. And as it turns out, okay, I'll draw you a little map here. Here's Nevada, let's say. Here's Las Vegas down here. Utah's right in here, right? All this part of Utah and most of this in Nevada, all the way down, and it kind of runs then into Arizona down this way. Here's Arizona down here. All of this area is known as a place, the structural terrain, it's called basin and range, and it's characterized by this sort of topography across there. That whole region has been extended 300%. So in other words, if it originally was 100%, you pull it apart 3 times, essentially 3 times farther. That's the sort of action that's happening in this region of the Great Basin or in the Basin Range. So that is Horst and graben topography. It's one of the more common sort of things that you see in extensional terrains. So that is an area, so normal faults, Horsts and grabens. Horsts are the up blocks, grabens are the down blocks, and of course that corresponds. The grabens are the basins, and the ranges, the mountain ranges, are the horsts typically. Okay, so that gets us down to number 18 here. So on 18, let me show you just a little bit more on structural geology here, and I think you'll be ready to go on to the final after this. And so you'll look at the petroleum, of course, after this, but this will be the last segment that I actually upload. I've been a little bit out of sequence on how I'm doing these. What I've shown you here is a shale, and then I'm showing a shale over here. It's a little bit thicker on this side, if you'll notice in that diagram. So here's my shale here. Here's my shale over here. There's supposed to be dashes on there, so that's the shale. Notice that it's thicker on one side and thinner on this side. Here's a sandstone here, and a sandstone above, and a big thick sandstone over in here. In fact, this is the hanging wall. Here's the foot wall over here. And so if the hanging wall has moved down relative to the foot wall, that's a normal fault. And it's a normal fault that seems to have had sedimentation over the top of it. If you keep having sediment going on while that fault is moving, let's say that the fault is moving down on that side, right? It's going down this way, but if you're below sea level and that's going on, there could be sediment that fills in that topography. And so what you're looking at here is a special type of normal fault called a growth fault. And so a growth fault is associated with sedimentation. It's a normal fault associated with sedimentation. So you'll get thicker successions on one side than the other of the actual fault plane itself. So that is a type of normal fault. Okay, we're getting into the weeds now. Number 19. You guys already know that this is an anticline. And you know that this is the shape of a syncline, right? And I mean, they can be overturned too. They could be, you could actually take these in a mountain range, you could flip these things over. So you always look for way up indicators is one of the key things that geologists look for. But that's only two of the main types of faults. So this is an anticline right here. Okay, I do a funny thing when I'm in class where I can get some classroom participation. It's a little bit like the YMCA sort of song, if you really recall, from the Village People, right? So YMCA, all that stuff, right? We get up and we actually stand up and say, here's an anticline. So we have our arms pointed down and we have our arms pointed up. For a syncline, it's a little like a sink. Anticlines with your arms away. So you get the idea about what the limbs are on each one of these. So what if we had a fold that had only one limb? And that's what I show you in number 19 here. It's only got one limb. We call that a monocline. That's another type of fold. It's not a real common one, except in places like the Grand Canyon. The Grand Canyon, as it turns out, has 3 or 4 of these things. And usually it's because there's some sort of fault in the subsurface that's going to do something like that. Some sort of high angle normal fault or almost a vertical fault, but where you get bending of the rocks over the top. So that's what a monocline is. That's real common in the Grand Canyon, but it's one of the few places that I know of where it's fairly common. So let's go on to number 20. Number 20 is what type of forces cause folding? Normally, it's going to be mostly compressional forces. There's always caveats in these things, right? If you were a more experienced geologist, you would realize that you would say that folding can occur almost in any situation, right? If you have the right circumstances, but normally it's compressional forces. So if you push something together, it's going to fold. So that is a fold right there. That would have been an anticline right there. Here's my syncline again, right? Here's a syncline form or syn form, and here's the form of an anticline. So that is compressional forces that lead to both of those, right? What type of forces lead to normal faulting? And again, I prefer that you would actually use your hands. And so here's my fault plane. So one of the things you have to learn when you're doing videography and you're not experienced at it is the camera times out at 30 minutes. So anyway, I just lost a little bit of my video here, but not too much. We're on question number 20, I think it is now. What causes folding? That was compressional forces, right? Number 21, what type of forces cause normal faulting? If you have a normal fault, hanging wall, foot wall, should be getting used to that now, right? So here's our foot wall and our hanging wall. Which way do they go? Well, the hanging wall moves down relative to the foot wall. That's a normal fault. So when you do that, you're actually pulling it apart. So that's tension that you're applying in this situation. So that is a normal fault, and you get extension as a result of that. That's number 21. Number 22, what type of forces cause shortening? That would be compression, right? So shortening is related to either thrust faulting or actually folding and things like that, right? So number 23, what type of rock is found in the Sierra Nevadas? The Sierra Nevadas rise out of the eastern side of California, kind of a gentle rise, and then very high mountains, some of the highest in continental United States, and so they're made out of granite. And so it's an ancient granitic intrusion. And so that would be like Mount Whitney. That's one of the largest. Mount Whitney is the highest peak in the continental United States. Okay, so there are higher ones, of course, in Alaska, but that's not part of the continental part. So Mount Whitney, they're made out of granite. Number 23, number 24, what type of mountains are the Grand Tetons? The Grand Tetons are quite unusual. So they rise out of the plains, essentially, and they rise above an area called Jackson Hole. So Jackson itself is a town at the south end of that, and if you head north, you'll be heading up towards Yellowstone National Park. So these mountains have actually risen up along a fault plane. So there's a fault plane that bounds Jackson Hole here, and you actually have a fault-bounded mountain range there. Absolutely stunning geology. So if you ever get a chance to travel's where everything is at, okay? And educate yourself into how this works, right? So that's the Grand Tetons. So the Grand Tetons, high mountains in western Wyoming. What type of feature, number 25, what type of feature is a xenolith? A xenolith is foreign rock, essentially, right? So a xenolith is what we came to expect in places that have deep-seated volcanics, where it would bring pieces of the mantle all the way up to the surface. It was one of our lines of evidence for what the mantle is made out of. Okay, so that is pretty much structural geology. And I have a passion for structural geology. I'm actually, by training, a stratigrapher. I study layers of rock and how people explore for energy resources and things like that. I'm still a conservationist, however, and an environmentalist as well. But those are resources that we have and that we use. And so this is the end of the segment that is right before petroleum geology. So view the petroleum geology, and that pretty much completes the course. I'm going to record probably one more video to culminate the course and to kind of do a little course wrap up, but it won't be until probably tomorrow that I get that recorded. So, or maybe later this evening, I don't know. We have a final coming up. You already know that the final is scheduled for the 13th of May coming up here. It starts at 8:45 in the morning, but that means that is when it's going to open up on Blackboard. I'll probably keep it open for longer than 2 hours in order to give you time to complete the exam. Of course, it's going to be something that is open book. Again, I don't have any other choice in that, really. So anyway, take advantage of that, I guess is what I would say. The answers are given to you for at least half of the exam. So pore over those and learn those. And the last bits here that we've talked about since April the 20th, those are the bits that are going to be additional in addition to what was on the first three exams, essentially. So anyway, I hope you enjoyed the course. I hope that you find geology interesting. I certainly did, enough so that I wanted to make my life doing it. I guess I would say I wish you the best of luck, and I wish you health and happiness, and I will assume that I'll give one more video recording to you, and if we need to, we can even open up a study session if you want. I don't know if you want that or not, so if you do, send me an email, and we'll try to get something on Zoom that way. All right, well, I'll talk to you soon. Thanks now. Bye.